In this video, we're going to talk about a concept called chemical equilibrium. This is a process when your forward reaction rates equal your reverse reaction rates. So all reactions are reversible. To reach equilibrium, the forward reaction needs to happen at the same speed as the reverse reaction. So this picture shows in part 1, we have A and B reacting with each other, or mixed together, but nothing's happened yet. The reaction hasn't started. We don't have products formed. The molecules are starting to hit each other, and the rate of the forward reaction is going to pick up. The reaction is going to happen very quickly moving forward. And what you make are C and D. So A and B starts to create C and D. So we're getting products formed. Collision of reactants is going to slow down. One, because a lot of the A and B is now converted into C and D. And C and D is starting to get in the way, so A and B can't run into each other as frequently. So the rate of the forward reaction is going to decrease, and the reverse reaction will start to happen. C and D will start running into each other and create more A and B. So that reverse reaction begins. Eventually, the rate of the forward reaction slows down enough, and the rate of the reverse reaction speeds up enough to where they're happening at the same time, at the same speed. This is what we call a dynamic equilibrium. Concentrations of all of your reactants and products are going to stay constant. This is not saying I have equal amounts of A, B, C, and D. It just means I'm producing A and B as fast as I am producing C and D, and the concentrations are no longer changing. It also doesn't mean the reactions are stopping. Okay, these reactions are still happening. They're just happening at the same rate that you can't see a change in concentration. Equilibrium can be represented by what we call an equilibrium constant expression. So the way we write this is we have to have a balanced reaction. We are always going to have products over reactants. KEQ is the equilibrium constant. It's this abbreviation for it. Anytime you see something written in brackets, it means concentration. So remember, with equilibrium, we're saying our concentrations aren't changing, right? We know what they are. They're not the same for reactants and products, but they're not changing anymore. So the way we do this is we're going to write the concentration of our products. So here's the concentration of C, and it's going to be times the concentration of D. So this is multiplication. Notice there's coefficients in the reaction, and there's exponents in the equilibrium constant. So your coefficients become the exponents on that substance. So for the products, I have A. So those were the products. Reactants, I have A, the concentrations on the bottom, and I have B. Its concentration is on the bottom. Again, coefficients become the exponents of those. So here is my equilibrium constant. Let's think about what this is saying. So I'm saying how much products I have divided by how much reactants I have. So if KEQ is a big number, that means the numbers on the top have to be greater than the numbers on the bottom. So that means I have more products than I do reactants. So if KEQ is very large, I essentially have all products, and we say the equilibrium lies far to the right, right? The products are on the right, reactants are on the left. If the KEQ is very small, that means the bottom number has to be bigger than the top number, and then that means I have more reactants than products. So we say the equilibrium lies to the left, okay? And this is all kind of degrees of it, right? Very large, more than 10 to the 30th, very small, less than 10 to the negative 30th. There's different layers in between. What I really want you to know is for KEQ that is greater than 1, it is product favored. meaning there's more products than there are reactants. If KEQ is less than 1, that means there's more reactants than products, or it's reactant favored. You would also say for product favored, it lies to the right, because products are on the right. For reactant favors, the equilibrium lies to the left. So we are going to practice writing our equilibrium constants for given reactions. So KEQ, remember, is always products over reactants. And then our exponents are our coefficients. So the other thing to keep in mind here when you write these is you're only going to use concentrations for aqueous and gas. If you have something that is solid or liquid, those substances are not included in your KEQ equation. So if I look at products for this first one, I have 2 NOs and a Cl2. So I've got concentration of NO, and it's going to be raised to the second power, times the concentration of Cl2, and it would be raised to the 1. We don't have to write 1. That then is over the concentration of the reactants, and I have 2 NOCLs. So NOCl raised to the second power. All of those were gases, so they're all included. So that is your KEQ equation for the first problem. If I look at the second one, products on top. So solid is not included, so I'll ignore that. We've got 4 NO2s, so I'm going to put NO2 raised to the 4th power, and then I have 1 O2 divided by reactants. Reactants are a solid, so those are not included. So you could just leave it as NO2 to the 4th times O2, or you can say that it's over 1. Either way, everything's over 1, right? So it's not wrong to write over 1. Number 3, products. We have an aqueous and an aqueous. They're both included. So CH3COOH, coefficient of 1. And then we have C2H5OH, also with a coefficient of 1. Reactants, the water is not included because it's a liquid. We will include the other reactant, also with a coefficient of 1. Last example, product is a solid. So that means I can't just leave the top blank. If all of your products are solids, you do have to say that it's 1 over something. So the 2 reactants are aqueous. So I have Fe 3 plus raised to the 1st power, because there's coefficient of 1, times OH minus raised to the 3rd, because the coefficient of 3. So there's your equilibrium constant for those 4 examples. There are ways to alter the equilibrium. So we talked about ways we could increase or decrease rate. Here we're going to talk about ways we can shift equilibrium to reactants or products, whichever we prefer. This is what we call Le Chatelier's principle. So Le Chatelier's principle tells us that all reactions at equilibrium can be disturbed in a way to cause the reaction to shift to either reactants or products in order to recover equilibrium. So what we're doing is we are basically saying somehow we're going to change the concentration of our reactants. We're going to change a temperature. We're going to change pressure or volume. So we're going to do something to our reaction that's already at equilibrium to upset it and cause it to either make more products or make more reactants. So if I change the concentration, the reaction's going to adjust or shift to consume whatever it is I'm adding. Or more to make whatever is removed. All right. So if I have A plus B makes C, and this is equilibrium, if I put in more A, so let's say I'm going to increase the concentration of A. Originally, it was already happy. It had the right amount of A, B, and C. But now I'm going to put more A in. If I increase the amount of A, it's not going to like that. It's going to do what it can do to get rid of what I'm putting in there. So if it wants to get rid of a reactant, it's going to react more to make more C. If I, for example, take away B, so if I take away some B, it's going to want that B back, so it's going to react more the other direction to make up for me removing B. So if I increase A, it shifts to the right it's to make more products. If I take away B, it's going to shift to the left to make up for that B that I took away. So that's just kind of a generic example. If I change temperature, it's going to depend on whether it is endothermic or exothermic. Like we talked about in an earlier video, we can think of heat as either a reactant or a product. And then we think about increasing or decreasing temperature the same as we do concentration. So if I have A plus B makes C and heat, this would be an exothermic reaction because heat is a product, it's being given off. So now if I increase temperature, it's like saying I'm increasing the amount of product, which means the reaction is going to use up that product and make more reactant. So it would shift to the left. Pressure and volume. So this only matters if you have gas as reactants and or products. So if you increase pressure, that's the same thing as decreasing volume. This means there's less room for the gas molecules. So the reaction is going to shift to the side that has less gas. If you decrease the pressure, that's like increasing volume. Now there's more room. So now it's going to shift to the side with more gas molecules. And we'll see a specific example of that here shortly. So this infographic by Compound Chemistry Compound Interest is a very good depiction of this. It shows you each of the things we talked about. We've got concentration, temperature, pressure. So your reaction's in the middle, okay? For concentration as an example, at the top it says you can increase the concentration of a reactant and then tells you what happens. You could change your product concentration and increase and it tells you what happens. Okay. For temperature, temperature increased tells you what happens. Temperature decreased tells you what happens. So this is a very nice summary of what we just talked about previously. So feel free to use it, read through it in more detail. Here's a specific example. So you're given a reaction, it's at equilibrium, and we want to decide which direction it's going to shift whenever we make the following changes. So number 1 says I'm increasing the concentration of C6H12. So if we look at the problem, C6H12 is a product, so I'm going to increase the amount of C6H12 that I have. That means the reaction is going to do what it has to do to get rid of the C6H12 that I've put in there. So that means it's going to react and shift and make more reactants by using up the products that I just put in there. So increasing the concentration of the product is going to shift the reaction to the left to make more reactants. Decreasing the concentration of C6H6. So C6H6 is a reactant. So if I take some of it away, the reaction is going to do what it has to do to make more, which again is shifting to the left to make more reactants. Increasing the temperature. So I'm increasing the temperature. In this case, heat is a product. So increasing temperature is like increasing the products, which again means it's going to shift to the left to use up that extra product. Decreasing pressure by increasing volume. So here I need to look at the number of gas molecules. So I have 1 of the C6H6s. I have 3 of the H2s, so that's a total of 4 gas molecules. On the right, I have 1 of the C6H12. So if I give myself more room, the reaction is going to shift to the side with more gas molecules, so it's going to shift to the left. Add a catalyst. Catalyst has nothing to do with equilibrium, so it's not going to change. A catalyst is only important when it comes to rate of reactions. So just a quick summary. If I increase the amount of a product, whether it is concentration or if temperature, or sorry, if heat is a product, so I increase temperature, the shift is going to be to the left. If I decrease the amount of a product, either decreasing a concentration or if heat is over there, it's going to shift to the right to make more product. If I increase a reactant, it's going to shift to the right to use up that reactant. If I decrease a reactant, it's going to shift to the left to make more of the reactant that I took away.